Welcome to the APL quest. See APL Wiki for details. Today's quest is the second from the 2015 round of the APL problem solving competition. We're giving some numbers and we are to find out what the longest run of intervals are, where the intervals are all increasing in value. Let's start with some test data. So, we are to find which intervals, that is, these spaces, so to say, in between numbers that are increasing. What we can do is we can subtract any number with a number before it. This is an n-wise reduce, and because of the direction we want the rightmost element minus the leftmost element, so we can use a negated window length to flip the subsequence backwards before we apply the reduction over it. There's a little catch that if, and this is one of the example arguments, if the input is a scalar, then the n-wise reduction will fail. But we can fix this simply by raveling the argument. Okay, so going back to our sample data, we got these differences, and we want to find out where they are strictly positive. So that would be any of them that are greater than 0. Now we have a Boolean mask indicating which intervals are growing. And then we can use partition on any data really, but conveniently we can use it on the same data. And the way partition works is that when the argument is left argument is Boolean, is that any runs of ones become segments, and any elements that are 0 get dropped out, and that's also where a new segment begins. So we can see how we are getting these groups of first the 1, and then the 0 drops out, another 1, and then the 0 drops out, and then we have the 3. And now that we have these segment lengths, these are the runs of growth. So we can simply take the length of each one and then do the maximum over that, and that gives us our result for this case, which is 3. Let's put this into a function like that. Right. There are some tricks we could do to make this shorter. Let's think about this. We're finding a difference, but we're not actually interested in the difference at all. What we're interested in is whether or not we are growing. So instead of comparing elements in size, we can just compare them directly. So we want to know if the left argument is less than the right left element is less than the right element in this 2-element sequence. So we can just do a two-wise less than reduction, and that would work as well. There are other, should we say, golfing tricks we could use to make this shorter, but that doesn't mean it's better. Just for the fun of it, let's try this. So let's say we have this vector of vectors. If we mix it, that is, we stack these vectors on top of each other to get a matrix, then we have to pad the short ones with zeros, but that doesn't actually matter. We can see what this looks like, and then we can see that the longest subvector is the one that determines the number of columns. So if we transpose, then the number of rows is going to be the original width, and that's the length of the longest one. So we could just tally that. Alternatively, you could get the second element of the shape, but this is shorter, just not better, because transposing can be a bit expensive. So for CodeGolf version, this works fine. But what is a good way of doing it? See, the problem is that we are partitioning into these subvectors, creating potentially a huge amount of vectors in a large vector. That's a lot of pointers and a lot of wasted space for information that we actually don't need. The only thing we really need is the length of each. And so let's think about it for a moment. Let's start off again with this comparison. What we want to find is the length of sequences of ones. Okay, well, let's normalize this by padding with some zeros around it. Now we can more clearly see these runs of ones that we want the lengths of. And now we know that we begin with a 0, end with a 0 as well. What we want to find out here is whenever we are switching from 0 to 1 and 1 to 0, that's a cutoff point. We just need to know the distances between the cutoff points in order to get the length of the runs. So we can attempt to do that. The cutoff points, the places where we switch from 0 to 1, 1 to 0, that's when consecutive elements are different from each other. 0 is different from 1, 1 is different from 0, and of course 1, 1 is the same, 0, 0 is the same. So it would seem that we can do this pairwise difference, and already now we can kind of see our result here. That would be this sequence here with 3. So we can take the indices where there are ones, and then we can measure the distance between consecutive ones. And then we can see our 3 over here. We might think that we can then just do a maximum here to get the 3. But if we try that, then we have fooled ourselves. And the reason for that is that, remember, here we're looking for the cutoff points between runs, but it would find the cutoffs between from a change from a 1 to a 0, and then back from 0 to 1, just as much as it will find what we're looking for from 0 to 1 and then 1 to 0. So we can illustrate this with an example that's not going to work well. So let's just have some lots of descending numbers here, but very little increasing numbers. And if we try this expression here, then we can see we get 7. And this is because if you go back and look at our differences, well, we can start off with this actually. We can see that here are our increase runs. And if you look at the where the differences are, then sure enough, there's a difference here. We go from 1 to 0 and then 0 to 1 over here. And then asking for the indices of that and the consecutive differences between them gives us the length of the longest run of identical items. But we only want the runs that correspond to that are all 0 runs. So this approach doesn't quite work, but we can modify it to make it work. Let's go back to our Boolean vector here. This indicates where we are growing. Now, instead, if we look at the opposite of that, where we are non-growing, then we get a bunch of 1s whenever we have a streak of 0s that is non-growing, and we only get 0s where we have a streak of 1s. Now if we ask for the indices and compare consecutive elements, then since every time there's 0 followed by 0, they are completely adjacent, that gives us a length of 2 in between, a length of 1 in between them, because it's just one element over the next one. Since we are counting the intervals, not the elements involved in these streaks, then we have overestimated by 1. So we'll just have to subtract 1, or estimate overcomputed by 1, and that gives us this 1 at the end, indicating the this original sequence of zeros, which is our growth. And so we can put this into a function, and we can try it on each of, well, we still need to take the maximum here of that. You can try it on each of this n and x, and that gives us correct result. 3 for the first one, and 1 for the example with a long decreasing streak, but a short increasing streaks. Then, before we give this a name, we can simplify some things. So let's just run it again every time we simplify some things to make sure that we're not changing anything. Notice here that we are applying a Boolean not, and that means instead of applying that not, we could just initially compute the values in exact opposite. So not less than is the same thing as greater than or equal to, and not on these zeros would be 1, of course. So we can get rid of that and see that we get the same result. Here is interesting. We are flipping around the subsequence before we're applying minus reduction. That is, since it's only an x2, so that's just b minus a instead of a minus b. That means if we don't flip it around, then we get negated values. So if we're getting negated values, then we have to subtract them from here. Finally, we could move this over, because here is a reduction over a bunch of numbers. All these numbers are being processed with -1 minus that. And since we're just finding the maximum, then we can do the addition, subtraction afterwards. Just have to remember that these numbers have been negated, so we don't want to find the maximum anymore, we want to find the minimum as a negative at that point. So this gives us a very nice solution that should be also efficient. Did I remember to assign B? Yeah, I did assign B. Okay, great. So so now we've got these 3 different definitions. And we've got the A, which is very much the way we think about it. We're finding the streaks, we're finding the lengths, we're getting the maximum one. There is one issue with A that we haven't taken into account, and that is, what if there aren't any streaks? And that's a bit of an issue. So let's try that on some decreasing thing like that, and that doesn't look right. Negative, well, kind of infinity, the smallest possible representable number. And that is because we are finding these partitions, and if there aren't any, that gives us a length 0 array. Getting the lengths of each one, still an empty array, and then we are reducing with maximum over an empty array. And that would give us the maximum function's identity element, which is negative infinity, or as close as we can get to that. And we can fix that simply by requiring that the length is at least 0. So let's reset that. And now we are ready for some comparison in performance. Let's generate some test data. I found it convenient to use 1,000 integers in some random permutation. That should give us about 5 on average as the longest streak of consecutive growth. Importing CMPX from the defense workspace, and then we're simply applying that to our test case. Right there. And if my predictions are right, then the golfed version is being exceedingly inefficient by creating this matrix that we don't need. So it's going to be a bit worse than the original solution, which was the more intuitive solution. And then there's the entirely flat solution, where we never create the partitions. We rather do the computation directly of them, which is going to be hugely more efficient. Definitely the one you want to go for speed. Thank you for watching.